topics you have great interest in, make sure you let us know, send us an email or somehow get to us, and we have contact information at the end here. But we try to do these, they're once a month, they're 1 hour, good topic. We do 3 little quick presentations for 10 or 15 minutes, and then about 15 or 20 minutes of Q&A. So designed to be quick and interesting. And then my name is Ron Ellis. I'm your moderator today. I'm a consultant and work in the Boston to New York area, usually up and down the coast here, and do quite a bit of work with brands, with printers. And also I'm a G7 trainer and a brand trainer for Idealliance. I have a lot of hands-on experience and do quite a bit with this. But let me get to our panel, because our panel are the real experts on these topics. They deal with them every day, especially the specific topic that we have today. Our panelists, we have David Hunter. He's from Pilot Marketing. He's been in printing and prepress for many, many years, going way back to companies like Aldus, and working with many, many large printers, large brands, and companies around the world. He's going to be talking and showing Chroma Checker and talking about how he tracks instrument alignment and how he's got these really neat matrices that show the difference between instruments and how they work, and especially within a supply chain, if you have a tight delta E, what does that difference between instruments mean? So he's going to talk about that. Danny Rich is a senior color physicist at Sun Chemical, and also very, very active within the standards community. So if anybody knows about standards and these type of topics and these obscure topics, he's probably the most knowledgeable guy I know, and even in our standards meetings, he's right up there at the top with the person who knows the most about many of the topics that we deal with. And also great to listen to, because he's great at, for how much he knows, he's very good at boiling it down to something that's understandable. Also, we have Jinkai from TeshCon. He's over on the left, because I didn't have a picture of him here, but you can see he's sitting here where the mouse is flipping around. That's Jinkai. He works for TeshCon. He's a color expert, graduate of RIT, and works for TeshCon. He's sort of their go-to guy for expert questions on instrumentation, measurement, and standards. So he's quite good as well. And this is actually him in a BrandQ class last week at Microsoft that we had. So what we're going to do, the sequence that we're going to do today, our topic is instrument alignment, the difference in instruments and how that affects your supply chain. And the big idea here is, if you're a brand and if you have a tolerance that's tight, like 1.5 delta E, but your instruments are already off between each other by 1 delta E, what does that do for your supply chain, and what does that do for what you're asking? So we're going to go through it, and Jinkai is going to talk about this instrument difference and why it happens and how you check for it, and what the story of that is. Danny's done quite a bit of work about testing and measuring and materials that you measure on, and being able to make sure that you can take care of that, and he's going to talk about that. Then Dave Hunter's done a lot of research and has lots of measurements on different instruments, and he's going to run through and cover that. So each of these guys will do 10 to 15 minutes, and I'll clip them right up at 15 minutes so that we get where we need to be. But they'll do 10 to 15 minutes, and at the end of 15 minutes, we'll have a 15 to 20-minute Q&A session, depending on how much time we have. So Q&A, you can send your questions in to Steve through chat as we're going, and he's going to tally those, and we'll ask him at the end. And we'll start right off, and I'm going to, before we do that, I'm going to say 2 words about BrandQ, which is sort of the program that is sponsoring this. BrandQ is a program that Idealliance runs with the main ideas of communicating, helping people understand how to communicate through their supply chain. So helping brands figure out what to ask for, and helping printers understand how to communicate back to the brands. Education, and a lot of times for brands, they don't actually know how to talk the language of print, and don't know how to communicate what they need and what's reasonable to ask for. Also validation, how do you tell if your supply chain is actually achieving what you want? So in the BrandQ program, we teach and work on all these topics. This is one of our classes. You can see here on the left, these are a bunch of print buyers, and they're basically going through and being trained, and you can see the sheets there. They're measuring, doing hands-on measurement with sample sheets. So they're in there learning, measuring, learning the language of color and what they can ask for and what are tolerances and how they work and those type of topics. They want to communicate. This is looking at some print samples there. These are one of the customers or brand owners brought in print samples of an issue they were having and discussing it in the class. And then validate, which is how we measure and understand if color is achieving the goals that we have. So that program is both online and we have live training several times a year. There's a link at the end here you can go to and learn more about it, or go to the Idealliance website and you can learn more about that. So I'm going to move right on. Steve, can you pass the presentation to Jinkai?
Okay, it's on its way.
Thank you.
And then Jinkai, up in the upper left where it says File, Edit, Share, just click, there you go, you got it.
Okay. Can you see my screen here?
Yes, just put it in presenter mode for your PowerPoint and you should be good to go.
Hello everyone, my name is Jinkai Chen. I'm one of the engineers at TASCOM. Today we are going to look at the causes of measurement differences from a device manufacturer perspective. It is quite common today to see print facilities with a mix of color measurement devices from different manufacturers. At TASCOM, making sure each device measures alike as well as matching to other devices are our top priorities. After years of talking to TASCOM customers, we have seen that there are two major reasons that can affect device measurements and instrument alignment. So first, we are going to investigate the device itself and the four terms used commonly when discussing measurements and instruments. Well, actually, there are 5 terms we must understand here. The first is called device centroid. The device centroid is a set of reference values that were established by the instrument manufacturer using a group of proprietary master devices. It is the end point for all product characterization and manufacturing. The black square in the middle represents the centroid, and the circle or ring around centroid is the production tolerance of devices. Repeatability is the ability of a device to reproduce similar measurement results when measuring the same sample over and over again. The graph on the right shows 5 measurements taken by the same TASCOM device on the same sample. Each dot stands for one measurement, and the closer the dots stay together, the better the device repeatability. The next term is inter-instrument agreement. The inter-instrument agreement shows how close 2 devices of the same make and model agree with each other. For example, if I measure the same sample with 2 TASCOM spectrodens, the distance between two devices here is the inter-instrument agreement. So if I use my pen here, so the distance here to here is the inter-instrument agreement. Now, if your workflow has a variety of measurement devices from different manufacturers, it is possible there will be some slight variations because of differences in the device optics, sensor resolution, centroid, etc. If I plot the centroid and tolerance of another device manufacturer, shown in red, then we take some readings with the other device 3. the distance between device 1 and 3 or device 2 and 3 is the intra-instrument agreement. So again, just using the pen here, that will be the distance from here or the distance to that sample. It's the intra-instrument agreement. So the reason I call it intra-instrument agreement is because they are pretty much the same type of instrument, but they are made by two different manufacturers. Okay. Now, if you have multiple devices, you should generally see sample measurements spread inside the ring evenly without any bias. When you notice a device is outside of the device tolerance range, that device should be put aside for some extra analysis. We are going to talk about how to evaluate and troubleshoot such a device later in the presentation. You should expect to see some color differences when comparing devices with different measurement geometry, such as 045 or spherical D8. Sometimes these differences can be small, and other times can be quite large, depending upon the substrate and other characteristics of the sample. Keep in mind, 045 devices are the standard geometry type for the graphic arts industry. You should always try to use this type of device. Now we are going to change this up and talk about why you might see measurement differences when using two of the same kind of instrument. Over the past few years at Tashkon, I have helped many customers when they have questions about measurements taken by our devices or just the best practices to measure color. This brings me to the recommended device operating procedure, or how you can evaluate and troubleshoot a device to see if it's truly out of tolerance. This information will also be helpful for brand owners who are defining color specification documents, which are used to prevent measurement errors from happening. Before taking measurements, users need to first select which aperture size fits their production needs the best. The table here on the right gives minimum and recommended aperture size based on different screen frequency or resolution. In general, try to avoid measuring low-resolution jobs with a small aperture, since it may not capture the true color of the patch. In other words, the bigger the aperture, the better, because it averages the unevenness of the sample by default. The measurement settings are very critical, since it tells the device how to calculate data, such as density, LAB or LCH, from the spectral reflectance data captured by the instrument. I have seen many print quality reports indicate the measurement settings that should be used during production. This is great because when communicating these settings, you lower the chances for measurement errors. Any mismatch in these settings will cause calculated data to vary. In the screenshot on the right, the device settings match with the color measurement conditions specified by the print quality report. Every spectral, regardless of the manufacturer, should come with a white calibration tile, which is used to perform device-wide calibration. The white calibration material is a serialized standard for each individual device, and it is used to correct measurement closer to the centroid. The picture here with the red arrow shows the white tile we use to calibrate SpectroDens4. We recommend you white calibrate your device at least every 12 hours or preferably every 8 hours or before any color critical job. If the calibration fails and cannot be fixed on-site, contact the manufacturer for service. Because paper stocks are somewhat translucent, it is important to control and standardize on a sample vector before performing measurements. This sample vector must also be used across your entire supply chain. Depending on if the job is printed double-sided or single-sided, you can choose to use either black backing or white backing, as long as the backing material complies with ISO 13655 standard. The graph here is an example of the white backing. The spectral reflectance factor of this material has to be between the minimum and maximum value, plus some other requirements as specified in the ISO standard. When either communicating color specifications or performing your own in-house instrument testing, it is important to consider that the sample being measured can also impact your results. For example, if you are measuring colors printed on a craft paper stock, like this, because the paper stock itself has a lot of color and texture variation to it, this means color sample printed on this stock will also have color variations. Therefore, this kind of sample does not generally make for a good test subject when evaluating an instrument repeatability or just comparing two instruments to each other. Instead, we would recommend finding a color sample that is printed on a higher quality substrate, like a grade 1 sheet. This kind of printing will generally have less color variation than printing on an uncoated stock with a rough surface. It is just important to be aware that color variations can exist in your sample, and you don't want this to impact your measurement consistency testing. Considering all of the above, if one device still measures differently than the rest of your devices, we would recommend checking the device with any spectral tools from the device manufacturer. At TASCON, we have a tool called SpectroCheck that device owners can use to check the accuracy of any TASCON instrument. Also, in the near future, we are going to release a new product that not only verifies the accuracy of your device, but also can optimize the device behavior back towards the calibration centroid and within the inter-instrument specification. Finally, all devices should be sent back for factory recertification based on the regular service interval suggested by the manufacturer. Thank you.
Interesting. I have a few.
Steve, I think I'm probably going to pass over the present back to you, right?
Steve, can you pass it over to Danny?
So thanks, Jinkai. I'm going to pass the controls over to Danny here. While he's setting up, just a reminder for everybody that if you have a question, you can ask at any time and put it right in the chat box. And then Danny, just there you go. Right, your screen is starting to come online right now. Perfect.
There. How's that?
Looks like you're muted, Danny, I think. There we go.
Okay, everybody ready? Can you see everything?
We are ready whenever you are. Yes.
Okay, good. So I'm going to sort of follow on from what was just presented for you. One of the questions that always comes up for me more than, what material device can I use to fix my problem is why do I have a problem in the first place? I mean, we had a really good discussion here of the various words, the terminology
Excellent. Sounds great.
that we've created in order to describe the differences. But why do they come up? Why do we get these differences? All right. So light sensors are nothing more than electrical devices. Electrical sensors have way more adequate uncertainty for industrial uses than any of us could possibly need. So I've shown here a set of different kinds of, these are just digital voltmeters. All right. So in the upper right hand, the orange one, that's a 4.5 digits. Its accuracy is 0.05% plus and minus 1 digit. The one next to it on the left, that's considered a high resolution instrument, voltmeter. That's 6.5 digits, 0.0035% accuracy. Below that is sort of a medium resolution, that's 5.5 digits, 0.01% plus 4 digits. And then on the right, bottom right, is a super high resolution instrument, that's 7.5 digits, 0.0009% accuracy plus and minus that one last half digit. That instrument is 9 parts per million accuracy. Okay? So when it comes to measuring the voltage of your car battery, we don't have any problems. Every voltmeter measures that the same 12 point whatever voltage it is. But there's no question. I can buy a fluke meter, these are 3 different brands here, they all measure exactly the same. Why is that? The reason is because voltmeters are calibrated against a Josephson junction. A Josephson junction, shown here, the constant K is equal to 0.048 something something something, 2 times the voltage of the electron over Planck's constant. That's a fundamental law of physics. There's no question what those values are. It's absolutely etched in stone. And we can see over on the right, I showed just a little picture of how you make one of these junctions. And it basically is a sort of a diode junction, except it has a barrier so the voltage can't get through. But when the voltage reaches a certain level, the barrier opens and the electrons can tunnel through. That's very, very predictable. It's described by fundamental equations in solid-state physics. That's how you get these kind of rules. There's a physical constant, a law of nature that controls how you calibrate electrical meters. What is the physical constant for our colorimeters? Anybody got a guess? The answer is the perfect reflecting diffuser, a theoretical concept that nobody has ever seen, nobody's ever tested. It's just an idea. Something which reflects 100% of the light that's incident on it, in all directions uniformly. So it doesn't matter what your instrument looks like, what its geometry is, nothing. It will measure the same value on that material. Golly gee, it would be nice if we all manufactured perfect reflecting diffusers instead of printed ink or put ink on paper. Because ink on paper doesn't work that way. So now, spectrocolorimeters, spectrodensitometers, they're going to have to convert the electrical signals from these photosensors into measures of reflectance factor. The standard used to calibrate a reflectometer, we heard about Techcon calibrating their instruments with some white standard that comes with it. I'm going to take exception to that. That's called standardization, not calibration. Calibration means to eliminate all of the uncertainties. Simply forcing the instrument to read that value, it doesn't eliminate any uncertainty. It carries uncertainties with it, actually. It introduces new ones. But it standardizes the instrument to a predefined scale, which has been assigned to that white standard. So here's some examples that I've captured for you here. each country has a national metrology lab that maintains all of the scales. So they have a specification of how long is a meter, how fast is a second, how much charge is in a volt, and so on and so forth. But they also have scales for reflectance. What is a diffuse reflectance? So they have two different materials they typically use. Polytetrafluoroethylene powder. It's just tamped down to a specific density, which is about 1 gram per cubic centimeter, and then it's measured. So it's very fragile surface. You can't pass it around easily, but they measure it. So here's pictures of a couple of different labs. This is, I believe, NIST and the PTB in Germany in this bilateral comparison. The bars on the outside, the lines, the sort of step lines out there at 0.01 and plus and minus 0.01, 0.05, something like that, that's the combined uncertainty of the national laboratories on measuring 45 degree, 0 degree reflectance. All right? So if you were to measure the color difference on that, that's probably about 5 or 6 delta E. So down below, we use the ceramic. It's a little wider. Ceramic's not as pristine as PTFE. So the differences are greater, and the relationship between the two labs is different on that material than it was on the pristine material. So these are the kinds of numbers that Techcon and X-Rite and Minolta get in order to use in their production line to build all of those centroids. So their centroids could be miles off. They could be tracing to the lab in the bottom over here with the orange, and we're all out here using instruments in the field with the red, tracing to the red dots. We're going to be different simply because we have a different laboratory from which we bought our primary standards. So typically our uncertainty, I left to drop the Y, our uncertainties here in a white reference tile is about 0.5%. The voltmeter is accurate to as much as 9 parts per million. We're good to 0.5%. That's why our instruments, when we measure the repeatability, it's almost exactly the same every time we take a reading. That is not accuracy. That is simply repeatability. That's how good the voltmeters in our instruments are. But when we start looking at differences from instrument to instrument, from one brand to another brand, that's what happens when we see that big ring that was in there. That's where that big ring comes from as we begin looking at all those different clusters, different instruments, different materials, and so on. So differences in white standard from region to region, not unusual. At one time, I did a study when I was in the instrument business, and I took the same material, which was a very pristine opal glass, which was the generally accepted best material for doing reflectance standardization. At the time, they've now moved over to PTFE, but this was an opal glass, specially designed opal glass. And I sent it to 4 different labs around the world. And I got 4 different numbers, and the range across those numbers was nearly 1%. I think it's a little better today, but I wouldn't guarantee it. CIE publication, differences here other than the white scale. CIE publication 15. In 1984, it recommended 5 nanometer measurement intervals. I'm sorry, that should be 1994. Oh, that was the first part. It recommended 5 nanometer measurement intervals and bandwidth from 380 to 780. Everyone ignored it. In 2004, it re-recommended the 5 nanometer interval and measurement. In 2006, CIE 176 recommended geometry changes and tolerances for 45 degree, 0 degree reflectometers. And by the way, notes the symbology here. That was also recommended in 2004, that we switch from the old slash notation, which means illumination in view, so it's a visual based, to the ISO notation of the colon.
Interesting.
Okay. The aims and tolerances now should be more strict even than those for a densitometer. The densitometer is a relatively coarse scale instrument. It should be 0 plus and minus a half degree, 45 plus and minus a half degree, and the window of measurement along each of those angles should be 2 degrees plus and minus half degree. Both influx, the incident light, and efflux, the emitted or reflected light. So all modern instruments tend to currently continue to provide 10 nanometer sampling at a much shorter interval range, often 400 to 700. People will tell you, oh, that's only that's the range of vision. Well, it's not. Visual sensitivity of the eye to optical power at 400 nanometer is not reached until beyond 740 nanometers. So you're a lot more sensitive to long wavelengths than you are to short wavelengths. So stopping at 700 is just silly. All of those magentas and maroons, they're all still reflecting light beyond 700. And you're seeing it, but you're not counting for it. So, some conclusions here. In the 1950s, department stores gave away yardsticks and printed scales. Today, they're sold in hardware stores, many times in cast aluminum, really nice, engraved scales. If you purchase your rules from the same manufacturer, they'll agree pretty well. And in most places in the world, however, these are meter sticks. The numbers on their meter sticks don't match the numbers on your yardstick. You can convert, you can do some things to correct it, but they don't, out of the box, they don't match. That's the same situation we've got in colorimetry today. So instruments from the same model and maker have pretty good agreement. How good is pretty good? We did a study when I was looking at this, and we took top-of-the-line instruments, and we had them in 4 different locations in the world. We sent the same reflectant materials, reference standards to them. They measured them. The agreement between the 4 instruments in 4 different parts of the world was better than 0.05 delta E. So instruments of different design, it's already been pointed out, or model or maker will not have such good agreement. There's no fundamental constant or physical example of reflectance factor to which makers can set their instruments. Spectral properties should agree with our visual ranges. If we're going to build an instrument to measure color, it should match what we see. It shouldn't just be made some way in order to make it inexpensive, or to make it easy to use, or to make it portable. Geometric properties should be able to compensate for the structures of the substrate. It was absolutely right. Substrates have a huge effect because our geometries are so sensitive to it. Our eyes don't that sensitive. We can get beyond that. There are ways to compensate for those. We need to be taking those into account. All right, so that's my soapbox for today. Why do we have a problem? Because we're not having any fundamental constants.
Amazing. Great presentation. Thank you. That was good. That was only 5 slides? Wow.
Yep. 5 slides. Sometimes a little is all you need.
There's a lot of...
By the way, did I give up?
That 5 slides is a lot of information.
All right, I pass the controls to David Hunter. Just up at the top, file edit share, choose my screen, David, and we'll can start. You're ready. And reminder to everybody, go ahead and submit questions at any time. We'll cover them at the end.
Okay, great. Thanks, Steve and Ron. So, and Danny, of course, and Jinkai. I'm going to try to take what Jinkai has told you and what Danny's told you, and kind of make it into some meaningful numbers. So this is a scale, 2 scales actually, and you can see very different numbers. And as we've talked about, instruments give us very different numbers as well. And we're going to get into some concrete details in terms of what these numbers are in my presentation, and hopefully it'll have meaning for you if you understand delta E. Here I show an assortment of instruments, and this is actually a formal presentation I gave about a year ago, which if anyone wants all the slides, I'll be happy to provide them. But the question always is, okay, which instrument is right? And as Danny said, there really isn't one right instrument in terms of the industry pointing to it and saying, this one's the right instrument, and this is how a color measurement instrument should measure color. So I actually did a number of key tests, right in line with what Jinkai was saying, related to what I'm calling within instrument precision, which is repeatability, and then between instrument, which he was calling inter-instrument, and then intra-instrument in terms of how different instruments are from one another. And as I go through some of these results, I'll just point out some factors here. And one of the key factors is, how does a measurement instrument measure color? And the target that I'm using is this Chroma Checker instrument inspector target, which has 42 different colors. And we chose these colors very scientifically to cover the entire spectral range, not only nanometer range, but also the energy range, to really take a fingerprint of how that measurement device measures color. I have seen manufacturers post information that my instrument A matches my competitor's instrument B on these 3 colors. Well, 3 colors is pretty easy to cherry pick which 3 you want to match, because some colors are better than others. So I tried to do an assessment over the entire range to really give us an idea of how that instrument's measuring color. And if you guys are familiar with DART targets, this all relates to the intra-instrument repeatability in terms of how consistent the instrument is to itself. Whereas this is test number 2, if you will, or inter-instrument, same instrument, but, same instrument manufacturer, but different model or different unit measuring the same colors. And then here is intra-instrument in terms of, okay, how different is my X-ray from my Teshcon, and how does it compare to what, let's say, my desired master instrument is? And for the numbers that I used, I'll compare it to an I1, since most people have an I1. Not that the I1 is the be-all, end-all instrument. It's not, but just from the fact that it's a very popular instrument. So I want to stress, backing is a critical component whenever you're measuring color. People say, yeah, when you measure your color, you should back it up with sheets of paper of the same type of paper stock. And that's not accurate. You shouldn't be doing that, because if I'm measuring on a very blue paper and you're measuring on a very neutral paper, right off the bat, our white point can be substantially different due to the backing. So we don't want the color behind the paper that we're measuring to influence the measurement itself. And in 2017, ISO updated the 13655 standard so that things like the I1 plastic tray that came with your I1, or even the IO backing on the IO, is out of date. It's not hitting the right standard. And this is important, because as we want to increase our color quality, we need to make sure our standards are correct. And we've actually manufactured a plastic backing. In fact, we just rejected a batch of plastic we got from the manufacturer because it didn't meet our specs. But this is an 11 by 17 plastic sheet, so it's very easily washable, and instruments slide over it very easily. So this is a new product that we've introduced and is really useful in the industry. Now, let's talk about the numbers. When we talk about an instrument and within instrument precision, this is using a device called a color muse. And I measured the same target multiple times, the 42 patch target multiple times, and assessed the delta E variation across those measurements. And I'm calculating overall that what we call the E factor, which is your 95th percentile cumulative relative frequency on this instrument, is 2.85. That's not the worst delta E. The worst delta E is actually higher than that. This is the 95th percent worst. And now, to be fair, this is a $59 instrument. Now, when I compare it to an I1, notice that the lines get much shorter or lower, so much lower delta E, and the E factor on this is 0.45. And if I look at an exact, here with my $6,000 exact, my E factor goes down to 0.15. So, as Danny said, you have different levels of precision in terms of the capabilities of the instrument, and this nicely quantifies what this means in relation to delta E. And if you understand delta E, then these numbers will have a lot of meaning, especially as I go through this scenario. In fact, here I call out names, I stack rank instruments and kind of show you where these different instruments fall on the table. And where it gets now more, let's say, multidimensional or a little bit more complicated is when you have multiple instruments comparing to one another. So each of these instrument manufacturers gave me 3 instruments, so I could do step number 2, which is the between instrument precision. And you see the numbers are much higher because when you start comparing how one instrument measures to another instrument, the differences stack on top of one another. And this can cause a real headache if you're trying to get a very precise and accurate result, because you see here, if my E factor's 6.5, I might be happy with this instrument. 6.5 is a significant difference, visual difference, and we can show you that. Here's 3 I1s in the same manufacturing batch, and you can see a 0.6 is a bit more reasonable. Now, I also did I1s in the non-same batch. So I took some random instruments and compared what they were, and you can see the numbers are in the 0.36 to 0.81 delta E range for the 95th percentile. And this is important because this is where it starts affecting, if I'm measuring a proof and you're measuring the same proof, but our instruments are different, which they are, depending upon that level of difference, that can influence how we're assessing that proof. And I'm going to get into those details in a few minutes here. So let me skip down and show instruments comparing to itself. Here's an actual example of an I1 where the customer was measuring this instrument once a week over the series of weeks, and then all of a sudden, one of the measurements, it popped way up. Now, you'll see the peak delta E is only 1, so visually, you would never know that this instrument is no longer measuring as precisely as it used to be. But by tracking it with our Chroma Checker software, it immediately alerts you to this problem and helps you understand that either you need to clean the instrument or you might actually have to send that instrument back to the factory. And by the way, this was traced back to a situation where the customer actually dropped it. He actually remembered that he had dropped it, and that's when the numbers started going big and he started getting red X's on his verification. I want to talk about, you know, as ISO standard says you should send the instrument back to the factory once a year. Well, that's a break-fix mentality. That's assuming that the instrument has been working for the last 12 months, and it's assuming that it might not be working now. If you move to more of a proactive assessment model of running your color department, using a tool like this to check your instrument once a week or once a month, you know when that instrument goes out, and so you know when it needs service. And if it doesn't go out, you don't need it to send it in because it is precise to what it's supposed to be. So it's kind of a change of mindset in terms of making this work. Now, in this test, I'm showing how different instruments compare against an I1, and in fact, how even an exact compares to an I1. And you can see, compared to an I1, that the 95th percentile, it's a 0.55 CRF, which, again, sounds pretty reasonable. But this is where making sense of the results comes in. What level of precision? Danny used the example of a yardstick. Well, obviously, we have some very precise tools to measure the precision for distance, and in the same way, we have this for color measurement instrumentation. Now, to my knowledge, Chroma Checker is the first program to implement this instrument gauge factor. This is a configuration you set in Chroma Checker that defines what percentage of your tolerance for your manufacturing do you want to give up to the instrument variation. And we follow 6 sigma rules here, and that we give you choices for 20, 25%, or 33%. And once you make this choice, now we can apply this to the delta E of your workflow. Meaning, if your workflow, if you're a brand color and you're trying to get 2 delta E match on your colors, then the instrument precision to itself should be less than 0.4, because that's at 20% of your overall tolerance. That means the within instrument variation has to be 0.4 or less.
That's great.
Ron, I'm sorry, you're really garbled. You're really garbled. Can you maybe text your question?
Oh, I wasn't. I was actually muted, but I didn't say anything.
Okay. Well, I'm hearing you, but it's kind of garbled.
It may have been some background noise from Jinkai. I muted Jinkai,
Okay.
and I'll take your back the question answer session. So continue on, David. It's great.
Okay, continue on. So this whole concept of an instrument stack and the error stack, E-factor stack, is really important because oftentimes you'll use one instrument to build the profile and another instrument to assess whether or not the printer that's printing to the profile is correct. And same with spot colors. Use one instrument for the spot color, but another, maybe an IntelliTrax on press, to measure that spot color. So understanding the effect of the instrument stack is critical here. And when we're calculating the instrument gauge factor with an instrument like an I1, now your workflows start getting to be some pretty big numbers. And especially if you're in different manufacturing batches. So for instance here, if I'm mixing multiple I1s, ideally, if this I1-4 is being compared to my I1, my tolerance has to be at least a 4 delta E, which most people, a 4 delta E is unacceptable when we get to brand colors. So it's important to know how your instrument measures color to itself, and it's important to know how your instruments measure color to one another. And in this way, I'm showing how ChromaChecker actually compares any set of instruments to any other set of instruments, and we calculate the workflow delta E. And the workflow delta E is what your tolerance has to be for your workflow in order to mix and match these instruments. And if you look at some of these numbers, they're very scary. They're in the 15, 7, 15, 11 delta E range. So it just tells you that mixing and matching instruments is a little perilous if you don't know the idiosyncrasies about the instruments. And here's another sample from a customer that was measuring how their Durst row printed color over the course of a year. And if you focus on the left and you look at the cyan, you would say, well, gee whiz, that cyan is 3 delta E different than the target. But it was 3 delta E on the first day that we started testing the precision of the printing device. Do you know why? They built the profile of the Durst row using a Barbieri LFP, and they're measuring the print every day using an I1. The way an I1 measures the cyan that a Durst row prints is 3 delta E different than the way the Barbieri measures the cyan of a Durst row. So if you don't think instrument differences are a problem, think again. We hear words like slight variation and, oh, there's a little bit of difference. Well, a little bit of difference to someone is a huge difference to somebody else. And so being able to quantify how your instruments measure color, not only to themselves, but to one another, is critical in order to build a color workflow that is going to meet your expectations through that supply chain. So at this point, I think I'm out of time. I've got just a couple slides that show, just to show that I'm not picking on Barbieri. Here's an I1 being used for proofing and an exact being used for press. And to mix and match these two instruments to get a uniform result, the expectation is a 5.8 delta E. Well, again, that's a lot. These are both X-rayed instruments. You would expect a better result here. And this is where instrument harmonization comes in. And we've built math within our software that can help compensate for how different instruments measure color differently. And we don't zero out the differences, but in this case, you can see we've improved the differences by 70%. So instruments are a critical component of manufacturing color correctly, and knowing how your instruments measure is critical to success. Thank you.
Yeah. Awesome. So, Steve, you have questions at this point, I would think. Let's move into questions.
Yeah, I'm going to turn the control over to you while I'm doing that there, Ron, in case you got like a slide you want to throw up, just throw up like a Q&A or a last slide. So everyone, if you have a question, just a reminder to type it into the chat box. And did I give you control, Ron? Let me see here. Yeah, there we go. Just type it into the chat box, and we'll ask your question here. It could be on any of the different presenters, any of the different topics at any time. So just type in the chat box. And also a reminder, everybody will be getting a recording of the webinar too. Look for that, in a day or so, maybe Monday, but sometimes we get it out right away. So just be watching for that. All right, so question I have here is, and anybody of our presenters can jump in and, take it, of course, is, here, another coming in fast. All right, so first question is, what changed with the backing with 13655 2017, colon 2017?
Danny, you want to take that one? Danny's the expert here.
Yeah.
I can repeat it too if you'd like.
No, yeah. I've heard it. In the earlier version, the backing was specified by some jaggedly sort of set of borders that were not indicative of real materials. So in the more recent version, in fact, that revision was started originally simply to refine the definition of the backing. And it was not our intent to exclude the I1IO white. I thought we had included it, but the boundaries now are made from real reflectance values for different kinds of white media. And there was a debate in the standards committee. We wanted something fairly white because the Japanese particularly use very translucent papers. And if the backing is too gray, then it reduces the color from their translucent papers. And packaging people in particularly North America had tested some, and they found if the backing is too white, when you put clear films over it, you get a lot of interreflections, and it makes for inconsistent results. So they wanted the backing not to be too bright. So we sort of compromised between those two extremes.
Okay, great. Next
and
question.
to clarify on top of Danny's message, the new I1s do conform to the new standard.
Yeah, it wasn't a big shift, but in terms of hitting the middle, but it did put some people's white plates out of spec.
Yeah. When you say new I1, what do you mean by new, Dave? What year?
The new IO. So I couldn't.
IO.
The new IO. The IO on the packing.
Yeah.
Yep. After 2016, right? Like you said. Okay.
Yeah. Yep.
Great.
Okay. Next question. We got some questions coming fast here. So, question is, And if I ask a question that I'm sharing in the panel side, if you want to pass on it or whatever, or that's always perfectly fine. A question here is, how much difference are the mechanics from a sheet fed, like an X-Rite ISIS Konica FD-9, to an I1? So mechanics from X-Rite Konica to an I1 sheet fed.
Okay, so I guess I'm not understanding what an I1 sheet fed is.
Like an ISIS.
Well,
An I1 ISIS.
Yeah.
Okay, so an I1 ISIS compared to like an IntelliTrax?
Let me repeat the question, and if we can pass, if you like, because we got a bunch of questions. I'm reading verbatim. How much difference are the mechanics from a sheet fed X-Rite ISIS Konica FD-9 to a I1?
Okay.
So that's like a handheld I1. Yeah.
Okay, so an I1 versus an ISIS or an FD9. So I've got all the numbers, and they're reasonable. I mean, you'll find more, the FD9 and the ISIS are much more precise than an I1. So they're actually more consistent to themselves, and they're actually fairly close to one another, FD9 and an ISIS. Mm-hmm. The I1, it's kind of a wild card because I've seen I1s that correlate pretty well with an FD9 and I1, and by that ISIS, I mean within an E factor of 0.6, but I've also seen them to be 2 delta E. So the I1's the wild card in that mix.
Okay. Next question here is, what is the easiest way to check instrument recertification information for like a Teton and X-Rite instruments? For example, the last recertification date, the next decertification due date, performance information, checking recertification information.
Yeah, so I believe that question is for me. So if you have any doubt or you're not sure, feel free to contact us and providing us your serial number so we can check that device in our database and tell you right away.
Okay. Next question here.
Another part of that, which probably relates to Steve. Steve, hang on one sec. I think another part of that, there's Steve, hang on one sec. There's instrument certification. David mentioned something about the breaking people. It's just the word in there was performance. David,
Hey, Ron, you're just totally breaking up, so we can't hear you, unfortunately.
Can you guys hear me? Oh, okay. So if I...
No.
All right. Maybe I type it in. Hang on.
No, we can hear you now, Ron. Try again.
Okay.
Try.
Yeah, okay. So the question was... Sure. The question was, that's instrument certification where you send it to the manufacturer. But Dave had mentioned the break-fix mentality in demonstrating performance versus just getting a certificate. Can Dave Hunter talk about that for just a second?
So I think you want me to talk about the fact that if you've got your device certified and then you test that instrument and assess it, let's say once a month over the course of a series of months, and you show and can prove that that instrument is not varying outside of your expectation or level of delta E tolerance, then there's no reason that you need to get that instrument sent back to the factory to be recertified. And this is up to each standards board, but we've worked with ISO groups in Europe and different countries as well as in the US, and when they've seen the evidence of tracking how an instrument measures color over a period of time, they've deemed that that is acceptable for meeting certification. Now, as I've said, each certification board that assesses ISO standards within countries can make their own decisions, but to date, we haven't had any issues related to that.
Yeah, but I think what Dave is saying is that for many people, sending it back doesn't necessarily assure that it's fixed if it wasn't broken already. And for many brands, they care about accuracy, not necessarily the certificate, although some care about the certificate.
And if I can add one more thing on this, is that depending upon how you're using the instrument, I don't see the instrument itself as being such a problem. It's how you're using it, which has to do with the backing, which we talked about, but it also has to do with the measurement condition that you're in. Are you measuring it in M0 or M1? And are you measuring it maybe even M2 because you've got a UV cutoff filter? And the application that's driving the instrument can actually influence how the instrument measures color as well. Now, not so much anymore, but really quantifying what you're doing in your environment with your instrument is really important, rather than, because usually there's something wrong in the procedure that's causing the color to be off. So the instrument might check out at the factory to be perfect, but you get it back and you're still having a problem, and it's probably something in your procedure that's off.
Yeah, great. Then there's the question from Alvaro. Do you guys see it?
Yeah.
Go ahead. Do you want me to read that one? My experience with the I1 has been that one.
Yeah, you should read it. Yes.
Yeah. All right.
Yeah.
Some I'm not sure. So my experience. This is the question. My experience with the I1 has been that there's a lot of spikes on the readings with my I1 Pro 2. When I do the same measurement with my Barbieri SpectroPad, I get much smoother readings. Should I trust my I1 Pro 2? Sounds like a Jeopardy question.
Yeah. So yeah, I blasted back. I thought that was directly to me and not to the group. But says, realistically, only Alvaro can make that decision. But if you're observing spikes in your results, so it's here one time, someplace else the next, that's an abnormal condition. As we pointed out, these photometer portion, the voltmeter portion of your instrument is much, much better than that. So if you're seeing those kind of spikes, then I would be concerned about it. But secondly, if it's spiking, how do you know that the measurement you just took for your most critical customer isn't a spike? So those are the times when you should be, calling your vendor up. In this case, the X-Rite, not Touch Context, but calling the vendor up and saying, "I'm observing this kind of data. I'd like to have you check this instrument out."
Great.
So Ron, we're
Any other
we're out of time, but if you saw a question in your inbox or something, or there's a couple more questions, but we could wrap up here, or.
Yeah. Did you say you had a couple more?
Yeah. We can empty them out.
Yeah. I mean, similar thing, because there was a question like, why does the I1 Pro 2 get all sticky? Alvaro asked that to us, Paula. Why does the I1 Pro 2 get all sticky? You can pass on a question if you like.
Sticky, I've never heard that one, so I don't know.
It could.
It could be the button. What type of food are you moving up there?
It sounds like it might be the button that's sticking, and I've seen this, that the mechanical button that depresses on the I1 sometimes gets old and just starts malfunctioning.
Oh, that's true.
That's a factory fix.
All right. Let me ask one last question here, and then Ron's got his contact information on there for everyone too as well. And then I'll give it back to you, Ron, for the wrap up. Question was, I had my older I/O table refurbed to fit the I1 Pro 2. Should they have changed the white base as well, since their standard is no longer valid?
It depends on when you sent it in. So that's going to be and they do charge extra for changing the base, at least from my experience recently. And Dave, a little bit more about that as well.
Well, no, I think you hit it on the head. It depends when he did it and whether or not he paid extra for the base.
Yeah, because they're going to charge you extra for a new base. So if you send it in just to have it checked, they'll check it. If you send it in and they change the base, they'll actually charge extra money for the base replacement. And I recently had it done, and I think it was $580 to do a conversion, and I think I paid another $200 to have the base changed or something. But I'm sure they quote it differently for every device. Yeah. So, panelists, thank you guys for all coming and giving your information. It was really good information, really great. You're going to get an email that has the webinar so that you could watch it again if you want to see parts of it. And also, we'll have contact information in the email for Jinkai, Dave, and Danny, so you can email those guys directly if you're interested in any of their products or questions or any of that type of stuff. A lot of knowledge these guys have, and it's great for them to take time out and actually put together, these little presentations, even though they're short. It takes a lot of time for them to do it. And we appreciate you guys taking time out of your day to show up and actually participate in this. So thanks very much, everybody. Appreciate it, and have a good weekend.
Okay. Bye.
Thank you.
All right. Bye. Thanks, everybody.
Thanks.
Yeah.